The exhaust emission standards introduced into Europe since 1988 define certain maximum limits for the exhaust emissions of vehicles. They relate in particular to the air pollutants arising in the engine during the combustion of the fuel: carbon monoxide, hydrocarbons, nitrogen oxides, as well as particulate matter. The graphs illustrate the development of the limits for heavy trucks and buses from Euro Standard 4 in relation to newly registered vehicles. Whereas it was still possible to satisfy the Euro 3 limits for heavy commercial vehicles through further developments inside the engine, it is only possible to fulfill the subsequent exhaust emission standards practicably from economic viewpoints with an emission control system. Suitable techniques for the exhaust gas aftertreatment are, for example, diesel particulate filters and SCR catalysts, where SCR is the abbreviation for selective catalytic reduction. Daimler AG decided at an early stage on the BlueTech diesel technology, which is based on the SCR emission control method. The exhaust emission standards Euro 4 and 5 can be maintained using this method. With the international introduction of the new energy generations in the model series OM47X, along with Euro 5 and EEV, the Euro 6 standard, which applies from 2014, can also be fulfilled. Due to the international deployment of the new OM47X engine generation in various vehicles, the exhaust emission standards applicable in the relevant countries must be taken into account. This applies not only to the limits themselves, but also to the exhaust gas cycles and measurement techniques. Even more stringent emission regulations than in Europe prevail in part in large industrial nations, such as, for example, in the USA or Japan. Conformance, even to these stringent emission regulations, is ensured by appropriate technical adaptation of the vehicles in the OM47X model series, which are deployed in these countries. For some years now, the BlueTech diesel technology has been employed in heavy commercial vehicles from Daimler AG to fulfill the European exhaust emission standards. With the previous Euro 5 commercial vehicles, the basic components in this technology consist of a high-efficiency engine and the SCR system with NOx monitoring. With the introduction of the OM47X engine generation, a new emission control system is being used. It also has an SCR system with NOx monitoring and numerous innovations with which you will become familiar in the course of this self-study program. But before we come to that, recall to mind the structure and components of the former SCR system, such as you know them from the two self-study programs, SCR of the BlueTech diesel technology and NOx monitoring. The illustration shows the corresponding schematic for trucks. Take a look at the principal function of the currently displayed SCR system in Euro 5 vehicles. The software required for operation and diagnosis is integrated into the engine control unit. Once the engine is started, a continuous flow of compressed air flows through the metering unit. The pump module is also supplied with compressed air. This is supplied by the existing compressed air system. At the same time, the pump module conveys the AdBlue out of the AdBlue tank via a supply line to the metering unit. The engine control unit controls the metering valve integrated into the metering unit. In this way, the AdBlue is exactly metered and then injected into the exhaust pipe through the injection nozzle. The NOx sensor after the SCR catalyst acquires the NOx content in the exhaust gas shortly before it emerges from the exhaust tailpipe into the ambient air. The sensor values are evaluated in the NOx sensor control unit and passed to the engine control unit via the SCR frame module. If the measured NOx concentrations exceed the limits stored in the control unit, the control unit sends an appropriate signal via the drive control system to the control unit of the instrument panel. Here the malfunction indicator lamp is actuated as a signal for the driver. As already mentioned, during the development of the new OM47X engine family, the emission control system was also adapted to the new engine design features. The AdBlue tank is now located on the left-hand side of the vehicle. Depending on the version, it can be arranged in front of or behind the fuel tank, or formed with it together as one unit with two separate tanks for fuel and AdBlue. In comparison to the former SCR system, some AdBlue lines are not heated solely by the coolant, but rather also electrically heated by heating elements integrated into the lines. The heating elements are actuated by the exhaust gas after-treatment control unit, independent of the temperature of the AdBlue in the AdBlue tank. The AdBlue pump module is located in the immediate vicinity of the exhaust gas after-treatment unit. An important new feature is that it is no longer connected to the vehicle compressed air supply, because the former SCR compressed air supply is omitted on the OM47X. The pump module possesses its own control unit, which switches on the delivery pump after the engine is started, thereby drawing AdBlue from the AdBlue tank. Here the AdBlue is brought to an operating pressure of 10 bar and is continuously applied to the AdBlue metering unit. There is a dedicated control unit, the ACM control unit, for the open and closed loop control of almost all functions of the exhaust gas after-treatment. It is located directly on the inner side of the exhaust gas after-treatment unit, and in appearance looks identical to the engine management control unit. The ACM control unit takes over the tasks of the former control unit, the SCR frame module. Along with the familiar NOx sensor, the SCR system has another NOx sensor. It measures the NOx concentration of the exhaust gas shortly before entry into the exhaust gas after-treatment unit. In comparison to the previous SCR system, the AdBlue metering unit now forms one constructional unit with the injection nozzle. It is directly bolted onto the exhaust gas after-treatment unit and is no longer connected to the vehicle compressed air supply. After the engine has started, the metering unit is continuously supplied with AdBlue, irrespective of whether AdBlue is being injected or not. AdBlue which is not required flows back to the AdBlue tank through the return line. The exhaust gas after-treatment unit is the main component for limiting the pollutant emissions. It is located on the right in the direction of travel. Moving it to the right side of the vehicle produces a very short path for the exhaust gases. In the Euro 5 version, apart from the various sensors, the exhaust gas after-treatment unit comprises the SCR catalyst and a following ammonia slip catalyst. Furthermore, the exhaust gas after-treatment unit acts as a silencer for reducing the noise emissions. The increasingly stricter exhaust emission standards and also the increasing demands of customers with regard to fuel consumption and overall efficiency, as well as the requirement to remain competitive going forward, were the primary reasons for the development of the new OM47X generation of engines. Since 2011 in Europe, the first representative of the new engine family, the OM471, has been deployed in vehicles such as the Actros 963. There are a number of variants of the OM471, namely for Euro 5, for EEV, and for Euro 6. Depending on the version, there are constructional differences, in particular with the components of the exhaust gas after-treatment unit. In contrast to this, the SCR system is the same with all engine variants. By the way, in this chapter and those that follow, the OM471 is presented as an example of the whole engine family. What characterizes the new engine generation with regard to compliance with the European exhaust emission standards? Let us consider the emission control measures with the OM471 in the Euro 5 and EEV versions. The inline six-cylinder engine has a common rail system with flexible multiple injection and injection pressures of up to 2,100 bar using pressure-boosting injectors. The high maximum injection pressure and extremely fine atomization of the diesel fuel in the geometrically optimized combustion chamber are crucial for very efficient combustion. Apart from the injection pressure, timing, and quantity, the rate of injection can be variably configured. Overall, this means for the first time complete control of the whole sequence of injection at any engine operating point. This leads to a quiet and soft start of the engine with smooth running performance, particularly low fuel consumption, and minimized exhaust emissions. 2 inlet and 2 outlet valves per cylinder enlarge the inlet and exhaust area to improve the turbocharging, gas exchange, and combustion. A new feature in comparison to the previous Euro 5 engines in heavy commercial vehicles from Mercedes-Benz is the cooled exhaust gas recirculation, the EGR. The EGR system has been developed with future exhaust emission standards in mind, and in the Euro 5 or EEV version has a lower recirculation rate and a smaller EGR cooler than the Euro 6 version. The cooled exhaust gas recirculation contributes to the reduction of nitrogen oxides already during the combustion process in the engine. The Euro 5 and the EEV versions of the OM471 also include an exhaust gas after-treatment system, which in principle corresponds to the previous SCR system, with NOx monitoring. You have already become familiar with the new features and constructive changes to the SCR system for the new OM47X engine generation. The exhaust gas recirculation, which is used for the first time in the OM471, consists of the exhaust gas recirculation actuator, the exhaust gas recirculation cooler, charge air pipe, and the charge air housing. The exhaust gas recirculation actuator controls the quantity of exhaust gas to be returned via the deflection of the exhaust manifold flap in the central part of the exhaust manifold. Internally, it contains an electrically adjustable mechanism, which is connected to the exhaust manifold flap via the adjusting lever. The exhaust gas recirculation actuator is connected to the engine coolant circuit through two pipes. The exhaust gas recirculation cooler is connected to the engine coolant circuit. It cools the exhaust gases branched off from the exhaust manifold in the exhaust gas chamber from a temperature of about 650 degrees Celsius to approximately 170 degrees Celsius. In the charge air pipe, the cooled exhaust gas meets the fresh air coming from the charge air cooler or the charged air and mixes with it. In the charge air housing, the fresh air mixed with the exhaust gas is distributed to the cylinders and passed for combustion. The graphics diagram shows the principle of exhaust gas recirculation. Here, exhaust gas is added to the fresh air. This results in the proportion of oxygen being reduced. The reduction of the proportion of oxygen causes a reduction in the combustion temperature, leading to a decrease in the emission of nitrogen oxides. And also the quantity of exhaust gas emitted is reduced. With a large mass of recirculated exhaust gas, however, the emissions of soot, carbon monoxide, and hydrocarbons increase due to lack of oxygen. The ratio between the mass of exhaust gas and the mass of fresh air must be specified such that sufficient oxygen remains for the combustion of the injected fuel in the combustion chamber. Since the exhaust gas recirculation on the OM471 is active over the whole range of engine speed, the ratio between the recycled amount of exhaust gas and the amount of drawn-in or charged fresh air must be precisely controlled. This EGR rate is calculated by the Engine Management Control Unit using a performance map. For this task, it needs the mass of fresh air and the mass of the recycled exhaust gases. From these two items of information, the control unit calculates the total mass of air passed to the engine for the combustion. To determine these values, primarily the signals from the following sensors are required: differential pressure sensor for exhaust gas recirculation, charge air pressure and temperature sensors in the charge air pipe, and charge air temperature sensor in the charge air housing. A further important sensor is the NOx sensor on the input of the exhaust gas after-treatment unit. It measures the NOx concentration of the exhaust gas shortly before entry into the exhaust gas after-treatment unit. The measured values are also used in the calculation of the EGR rate. How does the exhaust gas recirculation function in detail on the OM471? The exhaust gas recirculation actuator is actuated with a PWM signal by the Engine Management Control Unit, based on information supplied by the sensors. The position of the adjusting lever is influenced by the pulse duty factor of the signal, by means of which the exhaust manifold flap in the exhaust gas recirculation line is adjusted, and therefore the recycled amount of exhaust gas is controlled. The branched-off exhaust gas flows first through the exhaust gas recirculation cooler, where it is cooled down to about 170 degrees Celsius. Due to the cooling, the EGR rate can be significantly increased, because the density, and therefore the mass of the exhaust gases, increases with decreasing temperature. After the exhaust gas recirculation cooler, the exhaust gas passes through a connecting pipe to the charge air pipe. Here it is mixed with the fresh air, and then passed through the charge air housing to the individual cylinders for combustion. In order also to be equipped for future exhaust emission standards, such as, for example, Euro 6, further components relevant to the exhaust emissions are used on the OM47X engine model series. On Setra buses, a throttle valve adjusting motor is also installed in the charge air pipe. It is used for restricting the intake air during the active regeneration of the diesel particulate filter. The diesel fuel metering unit is located to the left on the engine and is supplied with diesel fuel through the low pressure circuit. It is used for providing the required quantity of fuel for injection into the exhaust pipe during the active regeneration of the diesel particulate filter. The fuel enters the component through the integrated shutoff valve. The pressure sensor on the inlet side measures the corresponding fuel pressure. The meter valve opens at defined intervals. The pressure sensor on the outlet measures the fuel pressure, which enters the fuel line to the nozzle unit, where the fuel is injected finely atomized into the exhaust pipe through the injection nozzle. Due to the high temperatures prevailing here, the nozzle unit is connected to the coolant circuit. The temperature sensor after the air filter is located in the intake air hose before the compressor inlet of the exhaust gas turbocharger. Apart from the overload protection of the exhaust gas turbocharger, the engine management control unit uses the signal for the calculation of the air mass, which is passed to the engine for combustion. On Setra buses, a speed sensor, which measures the rotor speed of the turbine wheel, is located in the center of the exhaust gas turbocharger. This information is used by the engine management control unit to protect the exhaust gas turbocharger from excessive rotational speeds. Euro 6 vehicles have, as well as the SCR catalyst, also a diesel oxidation catalyst and a diesel particulate filter in the exhaust gas aftertreatment unit. The exhaust gas first flows through the diesel oxidation catalyst. This has a number of tasks. Apart from reducing the carbon monoxide and hydrocarbons emissions, as well as the particulate matter, it is used for the oxidation of nitric oxide to form nitrogen dioxide. In the following diesel particulate filter, the soot particles contained in the exhaust gas are filtered out and stored. You will find out more about the structure and function of the diesel oxidation catalyst and diesel particulate filter on the following pages. What happens to the exhaust gas when it passes through the input pipe into the exhaust gas aftertreatment unit? First, it flows through the central pipe up to the end, where it is diverted by 180 degrees. Then the exhaust gas enters the double diesel oxidation catalyst. The two cylindrical inserts of the diesel oxidation catalyst each consist of an outer case of sheet metal. The actual catalytic element is situated inside. It consists of a ceramic carrier with many thousands of honeycomb channels through which the exhaust gas can flow. A porous intermediate layer, the so-called wash coat, is applied to the ceramic carrier. It enlarges the area by about 7,000 times. The actual catalytically effective layer consists of the rare metals, platinum, rhodium and palladium, which are very thinly vapor deposited on the wash coat. You're already familiar with the task and structure of the diesel oxidation catalyst. Now have a look at the function. By the way, the following equations are not chemical formulae, but rather schematic representations of the exhaust gas constituents reacting together. Diesel engines are always operated with excess air. Apart from the engine combustion products, the exhaust gas therefore always contains unburnt oxygen. It is used to reduce the amount of carbon monoxide and hydrocarbons. This produces carbon dioxide and water. For the most efficient conversion of the pollutants, a temperature of more than 260 degrees Celsius is required in the diesel oxidation catalyst, which is why the exhaust gas aftertreatment unit on the Actros 963 is fitted close to the engine. An important function of the diesel oxidation catalyst is the oxidation of part of the nitric oxide into nitrogen dioxide. A high nitrogen dioxide content is important for the following diesel particulate filter. Diesel engines have a relatively high level of particulate emissions. The particles are principally solid carbon particles, on which other exhaust gas constituents, such as hydrocarbons, are deposited. At higher temperatures, the deposits are partly released from the particles and are oxidized in the diesel oxidation catalyst. In this way, the particulate matter can be reduced by up to 30%. During oxidation of the hydrocarbons and the carbon monoxide in the diesel oxidation catalyst, heat is released. This heat is used to increase the exhaust gas temperature for the regeneration of the following diesel particulate filter. Once the exhaust gas has flowed through the diesel oxidation catalyst, it enters the double diesel particulate filter. The two cylindrical inserts of the diesel particulate filter each consist of an outer case of sheet metal. Inside is the actual filter element, which consists of a ceramic honeycomb of silicon carbide. The channels of the honeycomb are alternately open at the front and the rear, and separated from one another by porous filter walls. The walls are also coated with a range of rare metals. Now we'll take a look at the diesel particulate filter. The as yet unfiltered exhaust gas passes through the input channels into the honeycomb. Since the channels are closed at the ends, the exhaust gas is forced to migrate through the filter walls. The soot particles then remain clinging to the surface of the honeycomb filter, whereas the gaseous exhaust constituents penetrate the filter walls without any problem. Due to the high efficiency of the diesel particulate filter, up to 95% of the particles can be retained. Do you still remember the tasks of the preceding diesel oxidation catalyst? One of them is the oxidation of the nitric oxide to form nitrogen dioxide. In the diesel particulate filter, this now reacts on the catalytically effective rare metal layer at temperatures from 250 degrees Celsius with the deposited soot particles to give nitric oxide and carbon dioxide, which means that some of the deposited soot particles are burnt during the normal driving mode and therefore removed. This case is known as passive regeneration. Passive regeneration alone is not sufficient, however, and the particulate filter continues to save more soot particles with time, leading to an exhaust gas pressure drop on the diesel particulate filter. Therefore, the particulate filter must be continuously monitored with the aid of pressure and temperature sensors. When the pressure drop exceeds a certain value due to increasing soot deposits, active regeneration is initiated. You will learn more about this on the following page. The activation and duration of the active regeneration is decided by two factors. Firstly, by the pressure drop between the pressure sensors before and after the diesel particulate filter. Secondly, by a so-called soot model, which calculates the theoretical loading state of the diesel particulate filter based on the distance traveled since the last regeneration and the various engine operating ranges. Active regeneration can take place both during a journey or also at standstill. A prerequisite, however, is a temperature of more than 260 degrees Celsius before the diesel oxidation catalyst. The temperatures before, in, and after the diesel oxidation catalyst and the diesel particulate filter are therefore required by different temperature sensors. Both the pressure and also the temperature signals from the sensors are used by the exhaust gas after-treatment control unit to control the regeneration. Once the temperature exceeds 260 degrees Celsius, the control unit sends a request to the engine management control unit over the drivetrain CAN. This actuates the diesel fuel metering unit. This unit injects a precisely measured quantity of fuel into the exhaust pipe. The fuel mixes with the hot exhaust gas and burns in the diesel oxidation catalyst. Here the temperature rises to about 600 degrees Celsius. In the following diesel particulate filter, the stored soot particles are burnt to ashes. Whereas passive regeneration runs unnoticed in the background, with active regeneration, an indication of this, or in some cases a request for the driver to initiate this at the next opportunity, is displayed on the instrument panel. You will learn more about the indications and operation in the 4th chapter. When the diesel particulate filter has reached its storage limit and active regeneration is no longer sufficient, the filter must be cleaned or replaced in the workshop. By the way, on Setra buses, due to the longer exhaust paths to the exhaust gas after-treatment unit in comparison to trucks, and here starting with the Actros 963, additionally, a throttle valve adjusting motor is installed in the charge air pipe. This is actuated by the engine management control unit to reduce the airflow. The result is a mixture enrichment which increases the exhaust gas temperature. This ensures that the exhaust gas temperature before the diesel oxidation catalyst reaches the required level of 260 degrees Celsius, even when stationary. In the following, consider the interaction of the SCR components on the OM471, which is identical in the Euro 5 and Euro 6 versions. The AdBlue is stored in the AdBlue tank. Here there is also a level sensor and temperature sensor, which send their signals to the exhaust gas after-treatment control unit. The temperature of the AdBlue decisively affects the control of the coolant solenoid valve for the AdBlue heating. At an appropriately low temperature, it is actuated through the drivetrain can by the engine management control unit on initiation by the exhaust gas after-treatment control unit to thaw out any frozen AdBlue with the aid of the coolant which has been heated by the engine. After actuation by the exhaust gas after-treatment control unit, the pump module with the integrated SCR control unit draws the AdBlue out of the container and after filtering brings it up to an operating pressure of about 10 bar. Then the AdBlue is passed to the AdBlue metering unit. Both the AdBlue feed line and the pressure line to the metering unit are electrically heated as required. The metering unit is circulation cooled by the circulating AdBlue. The pressure and temperature sensors integrated into the metering unit measure the applied AdBlue pressure and the AdBlue temperature and signal this information to the ACM control unit. From this and further data, the ACM control unit determines the injection timing and the required quantity of AdBlue. The information is transmitted over the NOx can to the SCR control unit in the pump module. The SCR control unit correspondingly controls the valve in the metering unit. The AdBlue is injected through the valve directly into the mixing tube of the exhaust gas after-treatment unit. On the exhaust gas after-treatment unit, there are 2 nitrogen oxide sensors which measure the nitrogen oxide content in the exhaust gas. The first one is located on the input to the exhaust gas after-treatment unit, before the diesel oxidation catalyst. The measured NOx concentrations in the exhaust gas are passed on through the corresponding NOx control unit to the exhaust gas after-treatment control unit. This unit initiates as required control of the engine management, for example, of the exhaust gas recirculation, in that it instructs the engine management control unit to carry out the required corrections. The values of the NOx sensor on the input of the exhaust gas after-treatment unit therefore decisively influence the emission figures in the exhaust gas duct. The second NOx sensor is situated on the output of the exhaust gas after-treatment unit. It measures the nitrogen oxide concentration of the cleaned exhaust gases before they are discharged through the exhaust tailpipe into the environment. These values are used by the exhaust gas after-treatment control unit, for example, for the calculation of the quantity of AdBlue to be injected, and also for OBD purposes, that is, as proof of full conformance to the limits of the system. The temperature sensors before and after the SCR catalyst signal to the exhaust gas after-treatment control unit whether the SCR catalyst has reached the required operating temperature of at least 250 degrees Celsius. Directly after the SCR catalyst follows the similarly double ammonia slip catalyst, abbreviated to ASC. It ensures that any ammonia not completely reacted in the preceding SCR catalyst is not passed into the environment, because otherwise it could lead to unpleasant odors in the vicinity of the vehicle. The ammonia molecules are oxidized by the oxygen present in the exhaust gas using a special surface coating of platinum. This produces nitrogen and water. Additionally, a further coating with SCR functionality is present on the surface of the catalyst. Finally, the cleaned exhaust gas is passed through the exhaust tailpipe into the ambient air. The schematic illustration shows the complete emission control system on the OM471 in the Euro 6 version for trucks. All basic functions relevant to exhaust gases are monitored and controlled by the Engine Management Control Unit and the Exhaust Gas Aftertreatment Control Unit. Faults are stored in the onboard diagnostic system. You will learn more about monitoring and networking of the emission control system in the next chapter. Along with conformance to exhaust emission standards, the European emission control legislation also requires permanent monitoring of all exhaust-related systems during the driving mode. For example, the Engine Management Control Unit and the Exhaust Gas Aftertreatment Control Unit monitor and control the basic functions of the whole exhaust system. The illustration shows the networking of the corresponding control units with the Actros 963 as an example. The exhaust system includes not only the hardware components, but also the display units and controls in the cab, through which the driver can actively intervene in sub-functions of the exhaust system or monitor them. With the Euro 5 version, there are no significant changes in the display concept compared to the preceding vehicles. These have been described in the CBTs on BlueTech diesel technology and NOx monitoring. However, with the Euro 6 version, there are numerous new features and additional indicator lamps in the instrument. They signal to the driver all activities, needs for action, or malfunctions in the exhaust system. Causes of exhaust system faults which are indicated in the instrument may include primarily low AdBlue level, consumption of AdBlue too low, AdBlue injection interrupted, fault on monitored exhaust components, and fault in the exhaust gas recirculation. In the following, the display and operating concept for Euro 6 vehicles is presented in more detail. The malfunction indicator lamp, abbreviated to MIL, is a constituent part of the onboard diagnostics in vehicles. With Euro 6 vehicles, it is activated in the following operating states: during the lamp check, after switching on the ignition, and after the engine start to indicate exhaust-related malfunctions. On the following pages, you will find out more about the display states and their significance. The lamp check of the malfunction indicator lamp is primarily used for a quick check of the OBD system by public officials, for example during traffic checks. It starts with the switching on of the ignition and finishes with the starting of the engine. Note that the lamp check does not indicate any faults which affect the drivability of the vehicle. Furthermore, no faults are indicated which have to be repaired. The lamp check is divided into a total of 3 phases. The first phase is the display check of the instrument panel. Here the malfunction indicator lamp comes on for 5 seconds directly after switching on the ignition and then goes out for 10 seconds. The second phase of the lamp check is the operational readiness indication of the OBD system. Here a differentiation is made between 2 cases. If the OBD system has run through all checks once since the last time the malfunction message memory was cleared, the indicator lamp lights for 5 seconds and then goes out for a further 5 seconds. In this case, the indicator lamp flashes repeatedly for 5 seconds before again going out for 5 seconds. To understand the third, last phase of the lamp check, the so-called severity levels play an important role. Have a look what lies behind this. With the Euro 6 exhaust emission standard, a severity level scheme is being introduced for the onboard diagnosis. As with the 2 familiar NOx threshold values for Euro 5 vehicles, 2 threshold values apply in the Euro 6 severity level classification. These relate, however, not just to the NOx concentration in the exhaust gas, but also to the particulate matter. The lower threshold value corresponds in each case to the Euro 6 emission limits for heavy commercial vehicles. The second higher threshold value marks the OBD limit. If the emissions exceed the threshold values, the infringement is detected as a malfunction in the exhaust gas after treatment, and the malfunction indicator lamp is activated. The severity levels are being introduced for the purpose of classifying exhaust-related faults. That is, the degree to which a fault affects the exhaust emissions or the monitoring. A differentiation is made between the severity levels A, B1, B2, and C. Faults at level A have the strongest effect on the exhaust emissions or monitoring and lead to the OBD limits being exceeded. A fault at the level B1 can lead to the OBD limit being exceeded. Faults at the level B2 lie between the two threshold values and do not lead to the upper OBD limit being exceeded. Faults at level C have the smallest effect on the exhaust emissions or monitoring and do not lead to the emission limits for Euro 6 vehicles being exceeded. Now you're familiar with the severity level classification for Euro 6 vehicles. On the next page, you will find out how this affects the third and last phase of the lamp check. The third phase of the lamp check is for the purpose of displaying emission-related faults. The indication of the malfunction indicator lamp varies according to the type and severity of the fault. If no exhaust-related fault is present, the indicator lamp flashes at intervals of 5 seconds, each time for 1 second. The flashing cycle is repeated until the engine starts. When faults of level B1 are present, which have not been present for longer than 200 hours, the indicator lamp flashes 3 times within 5 seconds, and then pauses for a further 5 seconds. This flashing cycle also applies to faults of level B2, and is repeated until the engine starts. Faults of level A or B1, which have been present for more than 200 hours, are indicated by continuous illumination of the indicator lamp. By the way, faults at level C are not indicated. You now know that the previously described lamp check is used to give a quick overview for public officials during a traffic check. However, the main task of the malfunction indicator lamp is to make the driver aware of exhaust-related faults after the engine start or during the driving mode. Here too, there is a differentiation between the various indications depending on the type and severity of the fault. If no faults are present, the indicator lamp goes out immediately after the engine start. With faults of level B2 or a fault of level B1, which has been active for less than 200 hours, the indicator lamp illuminates for 15 seconds after starting the engine and then remains off. If a severe fault of level A or a fault of level B1 is present, which has been present for more than 200 hours, the indicator lamp is permanently illuminated after starting the engine. Depending on the type, severity and duration of the detected malfunction, appropriate indications appear in the event window in addition to the malfunction indicator lamp, as well as a further indicator lamp in the status area. If the driver ignores the indications, then a reduction of the available torque by 25% is imposed after 36 hours at the latest. If the fault continues to be present, in addition, a speed limitation is imposed. This limits the maximum vehicle speed to 20 km per hour and takes effect at the latest by 100 hours after the fault detection. Apart from the severity level, the activation and therefore the illumination of the malfunction indicator lamp also depends on the timing of the fault detection during the journey. Let's consider a fault at level A as an example. The schematic shows each journey symbolically as an arrow, and the timing of the OBD monitoring as a black spot. What effect does an exhaust-related fault have on the malfunction indicator lamp? When the fault is first detected by the OBD monitoring in the course of the journey, the malfunction indicator lamp is not yet activated. This avoids unnecessary activation of the indicator lamp for only briefly occurring faults in the exhaust system. The indicator lamp is only activated if the fault is still present during the next journey after the fault detection. Faults at level A are immediately indicated to the driver by the permanent illumination of the malfunction indicator lamp. If the fault is not rectified, the permanent illumination also continues during the next journey. If the OBD monitoring detects that the fault is no longer present in the current journey, then first for the 3 next journeys, the malfunction indicator lamp changes to brief continuous illumination for 15 seconds after starting the engine, before it is deactivated. And after that, no longer comes on during the following journey. Now take a look at the activation and deactivation of the indicator lamp based on a further example. This time for faults at level B2. As previously, with faults at level A, the malfunction indicator lamp is not yet activated when the fault is first detected by the OBD monitoring. If the fault is present in the next journey as previously, the status of the indicator lamp is set to brief continuous illumination. This, however, only takes effect at the next engine start, with the indicator lamp coming on correspondingly for 15 seconds in the instrument. Now look at the deactivation process once the fault is repaired. If the OBD system detects that the fault is no longer present in the current journey, the indicator lamp comes on again in the 3 following journeys, each time for 15 seconds after starting the engine, before it then no longer appears during the following journey. The AdBlue display concept for the driver for Euro 6 differs from the familiar display concept for Euro 5 vehicles. As an example, take a look at the displays in the instrument in the Actros 963. Here the level of the AdBlue tank is shown in a display independent of the fuel tank. When the level drops below 10%, an alarm indication appears in the event window, and in an additional text message, the driver is requested to refill with AdBlue. With a further reduced AdBlue level at a tank level of 7.5%, the same alarm indication appears as before. In addition, the driver is again requested to refill with AdBlue, because otherwise a power reduction will be imposed. If the AdBlue level falls below the 2.5% mark during the trip, an alarm indication indicates that the reservoir is almost empty. In addition, a yellow indicator lamp comes on in the status area. This also stays on after the message is acknowledged. An additional text display points out that once the vehicle is stationary, the announced power reduction will be activated if the driver does not refill with AdBlue. An alarm indication informs the driver that the engine output has been reduced. As you already know, here the engine torque available is reduced by 25%. In addition, the driver is once again requested to refill with AdBlue. Otherwise, a speed limitation will be imposed. If the AdBlue level drops to 0 during the trip, then the malfunction indicator lamp comes on permanently. Simultaneously, an alarm indication appears, which draws the driver's attention to the empty AdBlue reservoir. The impending speed limitation is again indicated by a further text message. This comes into force, however, the next time the engine is started, or with an engine operating time of more than 8 hours. That is, the driver still has an opportunity of refilling with AdBlue. In this case, the alarm indication that the speed limitation has been activated appears in the event window. As a result, the vehicle speed is limited to a maximum of 20 km per hour. In addition, the driver is again requested to refill with AdBlue. Take a look at what happens after refilling with AdBlue when the speed limitation was previously active. After switching on the ignition, the speed limitation is still active as before and is indicated in the event window. The malfunction indicator lamp and the additional indicator lamp in the status area also illuminate. After starting the engine, the speed limitation is deactivated and the text display cleared. The additional indicator lamp in the status area also goes out. In contrast, the malfunction indicator lamp lights up permanently during this journey. For the next journey, the indicator lamp only comes on for 15 seconds after starting the engine and then goes out again. This is repeated for the next journeys before the indicator lamp goes out completely at the latest after the 3rd journey, and no further detected faults. In comparison to Euro 5 commercial vehicles, Euro 6 commercial vehicles have a diesel particulate filter. You have already become familiar with the structure and function. The loading state is permanently monitored for proper operation by the ACM control unit. If this exceeds a certain limit, the MCM control unit starts an active regeneration, which can be started automatically as well as manually. A regeneration is, however, only automatically activated if all operating conditions, such as sufficiently high engine oil and exhaust gas temperatures and a sufficiently high engine load, are fulfilled. In order to inform the driver that an active regeneration is currently taking place, it is indicated by a green indicator lamp in the instrument. If one or more operating conditions are not fulfilled, the regeneration is interrupted prematurely by the system, and the indicator lamp goes out. It starts automatically once all operating conditions are fulfilled. Depending on the vehicle profile and operating state of the vehicle, it is possible that the active regeneration of the diesel particulate filter may not be able to be initiated automatically due to some operating prerequisites not being satisfied. For example, this is the case when the vehicle is mainly used for short-distance driving or low-load operation. Also, for safety reasons, an active regeneration is not automatically triggered when the vehicle is stationary. In these cases, a further indicator lamp and additional messages in the event window request the driver to initiate the regeneration manually. You will learn how this occurs on the following page. First, take a look at the display concept in the instrument, which indicates the loading state of the particulate filter in 4 stages. In the first stage, the indicator lamp lights up in the color yellow, and a notice about the increased filling level appears in the event window. A supplementary text also requests the driver to initiate the regeneration. What would happen if the driver doesn't manually start the regeneration within the next 4 hours, or no motorway or long-distance driving with increased engine output is undertaken in this period, which would be sufficient for automatic regeneration? In the second stage, along with the indicator lamp, the warning message is also displayed to the driver that the filter is now full. In addition, the driver is requested to immediately initiate regeneration, because otherwise a power reduction will follow. Now the driver still has about 30 minutes to respond to the request before the third stage is reached and displayed. In the third stage of the sequence model, the yellow indicator lamp flashes, and as well as the notice about the full particulate filter, the information appears that the engine output has been reduced. This restrictive measure is intended to persuade the driver to manually initiate an active regeneration now, at last. In the fourth and last stage, manual regeneration is no longer possible, which is why the indicator lamp lights up red. In the event window, the driver is also requested to visit a workshop, where the particulate filter must be cleaned or replaced. Continued driving is only possible with reduced power. Now we'll take a look at manual regeneration of the diesel particulate filter. The display in the instrument shows as an example just the second stage. That is, the driver still has about 30 minutes to manually initiate a regeneration before a power reduction occurs. Note that manual regeneration can only take place with the vehicle stationary. Here it is essential to note the additional requirements according to WIS and in the current operating instructions for the vehicle. Before manually initiating the regeneration process, it must also be ensured that the vehicle is not located on combustible ground or ground that is sensitive to heat. The driver can initiate the regeneration by pressing a button in the modular switch panel. If all conditions for the regeneration are fulfilled, the green indicator lamp lights up and informs the driver that the regeneration has been activated. This increases the engine speed. The whole regeneration process lasts between 30 and 60 minutes. During the regeneration, the vehicle must not be left unattended. Regeneration in a vehicle hall is possible in principle, but suitable extraction equipment has to be used for reasons of workplace safety. After regeneration, the green and yellow indicator lamps go out, and the warning message in the event window is cleared. In addition, the engine speed is reduced to the idling speed. By the way, preventative or premature regeneration of the diesel particulate filter is not possible. Manual initiation of regeneration is therefore always only possible once an appropriate warning message appears in the instrument. An active regeneration can be interrupted or blocked at any time if required, using a further button. In the instrument, you can now see an example of a running regeneration, which has been automatically triggered by the system. You can recognize this, by the way, because only the green indicator lamp is lit. On pressing the button, the green indicator lamp in the instrument goes out, and the regeneration is interrupted. Blocking is from now on only signaled by the indicator lamp in the button. Note that thereafter, excessive soot deposits in the filter are possible. This is indicated by the previously described 4-stage sequence model and the corresponding warning notices in the instrument. Blocking of the regeneration is also logged and stored in the malfunction message memory. The blocked regeneration is also retained after the engine is switched off, and with a following restart, and is not deactivated autonomously. This means that both the automatic and also the manual regeneration cannot start before blocking is cancelled by pressing the button again. The cancellation of blocking is signalled by the indicator lamp in the button going out. After that, automatic or manual regeneration of the diesel particulate filter is again possible, and the automatic regeneration shown in this example can continue provided all operating conditions are fulfilled. After repair work on the exhaust system, the malfunction code in the control unit must be cleared in an authorized workshop, and the torque or speed limitation be deactivated. With Euro 5 commercial vehicles, the resetting of the malfunction code and the deactivation of the torque limiter is carried out with the aid of Zentry and VDOC. With Euro 6 commercial vehicles, a fault can be cleared directly with Zentry after conclusion of the repair. Note that the lamp check initially still indicates the fault until the OBD system has detected that there are no faults after a certain number of test cycles. If the repair work is concluded without clearing the malfunction message memory, for example during roadside assistance, the fault can be also reset by the detection of fault self-healing.